Okay, so let's just finish up the slide that we were talking about on the previous video. So here, just remember when it says to describe the scatter plot, you are going to do two things. You are going to do the form, direction, and the strength, and I would suggest putting them into one sentence just to make your sentence a little bit shorter. So you're always just going to choose from the strength. Is it strong, moderately strong, or weak? And we say strong, moderately strong, or weak. That's like saying, strong is like saying it closely follows a line. It kind of gathers about a line, and weak means the data points are all over the place. And then, or if you were talking about a curved line, does it definitely follow a curved direction? Is it kind of follow a curved direction, or are they all over the place? Negative is like basically having a negative slope. Positive is like having a positive slope. And then the form is always curved or linear. So just make sure when you're describing strong, moderate, or weak that you're describing it based on whether it's curved or linear. Okay, let's take a look at the next example. So we want to describe this scatter plot. So remember, when you see the word describe the scatter plot, you make sure that you're going to do form, direction, and strength. So notice what here we're comparing points per game to the number of wins. So in general, it appears that teams score more points per game and have more wins, and teams that score fewer points per game have fewer wins. So that's, if you look at this, this is like a positive slope. So therefore, there's a positive association between points per games and wins. What would the form be? Let's take a look at what it looks like. Is it curved? Is it linear? There seems to be a linear pattern. So I could kind of draw a line and the points would follow that line. So there's a linear pattern in the graph. What is the strength? So strength means how, when you were to draw a line in, how closely packed around the line are they? Here, the points do not vary very far from the linear pattern. So since they don't vary very far from the linear pattern, we're going to say that that's a strong linear relationship. And then let's take a look. Does there appear to be any outliers? And remember, like I said before, this is just a matter of opinion. There does not appear to be any values. I don't see anything that's really far away from the rest of your data. Okay, so let's describe the scatter plot from the McDonald's question. So remember that this was comparing the amount of sodium to the amount of fat in a particular item off the McDonald's menu. Okay, so remember, describing your scatter plot is we're going to do form, direction, and strength, and then we're going to check to see if there are any outliers, okay? And that was where remember we got that DOFs from. Direction, outliers, form, and strength. So in this one, if we notice, there's a positive association, and notice how you have to put it in context at some point, between sodium and fat. The overall association is nonlinear, so I can't draw a nice straight line here. I don't really see, maybe it's a curve, okay? However, the association is fairly strong as the points do not deviate from the nonlinear form. So kind of it's like saying, maybe if I draw a curve like this, they're going to sort of closely follow that curve. Finally, there's 3 distinct clusters of points. So if you notice, there's a cluster of points here, here, and here, okay? And within each cluster, there's a positive linear association between sodium and fat. So if we're going to look at these individually, each of them would have a pretty strong linear relationship. However, we're looking at the overall pattern is not necessarily linear. Now, what exactly does a scatter plot do? A scatter plot displays the direction, the form, and the strength between, be careful with this, it's always 2 quantitative variables. So remember, something I can do math with. Linear relationships are important because a straight line is a simple pattern that's very common to follow. Unfortunately, our eyes are not good judges of how strong the linear relationship is. So we're going to use a numerical value that you're going to get from your graphing calculator to tell us how strong the linear relationship is. So I'm sure you've heard of the correlation R before. Now, keep in mind, when we talk about R, we're only talking about the direction and strength of a linear relationship. We're not talking about R, whether it's curved or whatever. We're only discussing R between a linear relationship. So remember, R is going to talk about direction. So is it a positive or a negative? okay, like positive slope or negative slope. And then strength is going to be how closely does it follow the linear pattern. R is always going to be a number between -1 and 1. R is greater than 0 is a positive association, less than 0 is a negative association, so that sort of follows your slope. Now, values of R near 0. So think about strength. If something has a strength of 0, that's going to be a pretty weak linear relationship. Your dots are all over the place. The strength of the linear relationship increases as R moves away from 0 and towards -1 or 1. So if you think about this, the strength of -0.75 is going to be the same as positive 0.75. This one's just going to be going down and this one's going to be going up, okay? So the closer it is to -1 or 1, the stronger the linear relationship you're going to have. The extreme values of R equals -1 and R equals 1 are only when the graph is perfectly linear. That means there is no deviations from the linear pattern whatsoever. So let's just take a look at what some graph looks like. So here, notice we have a correlation of 0. So your points are all over the place. Here we have a correlation of -0.3. So if you draw a line, it's kind of going down, but the points aren't very closely packed around the line. A correlation of 0.5. So this is about, moderate. If I draw a line, I got points above and points below, but they're not super tightly packed. -0.7, I have a negative relationship. They're a little bit more closely packed. And then take a look at this one. All of these dots are very close to each other, so that's going to give us an R value of 0.9. Here's where it's almost -1. All of those dots or all of those points are very close to the line. They're very tightly packed together. So if you take a look at this right here, this will give you your general rule of thumb whenever you're deciding whether it's strong, moderate, weak, or no correlation. And then just keep in mind, so for example, if it's -0.3 and 0.3, that's the same thing. And -0.3 to -0.5 is the same because one's just going up and one's going down. Okay, so if you'd like to get some practice at guessing the correlation, go ahead and click on this website right here. You'll be given a scatter plot and you'll have to try to guess what the correlation is. Take a minute and see how you do. Now, let's get back to the track. So let's take a look at an example of correlation. Each member of a small statistics class ran a 40-yard sprint and then did a long jump with a running start. I don't know if any of you are track runners in here. Here's the scatter plot of the sprint time and the long jump distance from data that we had earlier. Okay, so for example, right here, if we had, this was their sprint time, so maybe 6.75, and then this is their long jump over here would be in inches. So that's what that point represents. The correlation R is -0.84. And remember we said R measures the direction and it measures the strength. So that negative is going to tell us we kind of have like a negative slope or a negative association. So as the sprint time decreases, the long jump increases. And think about sprint time. You want to be faster, so you want your time to decrease. So let's take a look at the questions and see how you do. So I want you to interpret the value of R in context. So what does R mean? So include direction and strength in context. So direction and strength according to sprint and long jump. And then I want you to take a look and see what effect do you think that this highlighted point in red has on the correlation. So go ahead and see if you can try that and then come back to the next slide to see the answer. Okay, so let's take a look at what that correlation of R equals -0.84 means. So that's going to confirm what we see here. So notice we are doing three things. We are saying there is a strong negative association, and then in context just means tell me what it's between the sprint time and the long jump. So nothing fancy, just choose the two words, strong, moderate, or weak, and then positive or negative association, and then tell me what it's between. Okay, now let's take a look at this next one. Look at this data value right here. This highlighted point is a little bit higher than the rest. So we would think maybe if I had a point all the way out here that it might actually be a little bit lower. All right, so because it's higher than expected, it makes the correlation closer to 0. So basically what it's saying, if I was to draw a line right here, okay, if I'm drawing that line and this is your line of best fit, what this red line, this red dot is going to do is that actually is going to pull it away from where it should be. So what that's doing is that's actually making the R value closer to 0. So it doesn't mean it's going to change the correlation a lot, but it just means it's going to make it a little bit weaker. Now, the formula for R is a little bit complex, so you are never going to have to be able to do this by hand. You're always going to get this from your graphing calculator. Okay, so if you take a look, here is how the correlation of R is calculated, very complicated. 1 over n minus 1, so that's your sample size. And then basically take a look at what you're doing here. You're taking your x value minus the mean x value divided by the standard deviation of x. Then you're so this is like an ordered pair, x1, y1. And then you're taking the y value minus the mean divided by the standard deviation. You're adding it to every single one of those ordered pairs that you have on your graph. Your calculator does that for you. So it's the average of the products of the standardized values for x and y. So that's a lot of words going on right there. But you don't have to worry about that. Just get it from your graphing calculator. Now it's standardized. So basically what that's telling us is it's telling us how far above or below the mean data point is. So if you notice right here, so if we're taking our data point that we collected minus the mean, we're saying, hey, how far away from the mean is that data point? And then we're dividing by the standard deviation. So notice basically these are all z-scores. So this is like your z-score for x times your z-score for y. And then we're doing that over and over and over again. So a couple facts about correlation. So number one, it makes no distinction between the explanatory and response variables. So that just means if we have sprint time here and I have my long distance jump here, okay, if I were to switch them, I would have the long distance jump here and the sprint up here. So we said that this was a negative correlation, right? So as the sprint time increases, your long distance time or your long distance jump decreases. So if we notice, what's going to happen is as the long distance jump increases, your sprint time is going to decrease. Okay, so short, long distance, long sprint time, that makes sense. Long distance, shorter sprint time. So it's going to stay exactly the same even if you switch the x and the y axis. It's quantitative, so that means, remember, we can do math with it, take an average. Okay, R is standardized. It has no units. Remember, we said that R was basically like the same thing as a bunch of z-scores, all right? So it has no units. It's just a number we use, okay? So if you change the units, it's not going to change R. So let's say that this sprint was in seconds, and then the long distance time or the long distance jump was in inches. If we change the long distance to meters and we change the sprint time to seconds or left it as seconds, it will still stay exactly the same. So if R is greater than 0, there's a positive correlation. Less than 0, negative correlation. Ranges from -1 to 1. The closer it is to 1 or -1, it's a stronger correlation. It's closer to a perfect line. Like the mean and the standard deviation, remember, all those R values came from the mean and the standard deviation. It is not resistant to outliers. So what's an outlier? An outlier is just a point that falls outside the overall pattern. And this is not something that you're going to be able to calculate. You're just going to have to look at your data and say, hey, that could potentially be an outlier. And I'll show you how to, see how it affects R to determine whether or not it's an outlier, but there's no set formula when you're just looking at the graph. Now, an influential point, you're actually going to have to redo R to see if something is influential. So an influential point is when this point is removed, it will actually change your R value and the slope of the regression line. So it does have a major impact on the slope and the regression line. So keep in mind, correlation does not imply causation. We're only talking about a linear relationship, not a curved one. If it's close to -1 and 1, it does not guarantee a linear relationship. You have to plot the data to make sure that it is linear or curved, okay? So be careful, okay? We're always talking about R as a linear relationship. You must plot it in order to verify that it's linear. It's not a complete summary, so we're still going to be giving the mean and standard deviation of X and Y. It just tells us the form and the strength. I'm sorry, it does not tell you the form.